Thanks, Sam, for the fantastic presentation, and thanks everyone for gathering here today. My name is Theo, and I'm from the University in Melbourne. And to continue our discussion around the fields of autonomous vehicles, me and my colleagues work on a new navigation strategies for robots in general and autonomous self-driving cars specifically. And we call it the virtual traffic lights for multi-robot navigations, decentralized planning with centralized conflict resolutions. Or in short, we are introducing giveaway rules for robots. And before we dive a little bit deeper, we're going to start with the motivations behind this. In navigation strategies for autonomous vehicles, there are two common approaches. We have centralized system and decentralized system. For centralized system, we can imagine it like a one big brainer that controls all the smaller robots or cars in this regions. It knows about where the cars are going, it knows where, which path they're choosing, what is their destinations. And for decentralized systems, the cars have their own brain. They basically can plan on their own, know which path is best for them. And each of these approaches have their own pros and cons. For a centralized system, it is good for it can achieve optimal global solutions, good if we are in a shared goal. But one of the drawbacks is the computational complexity and single point of failure, because we demand heavily on that processing brain, like the big one, the big brain. But as for a decentralized system, we have greater scalability and robustness, but also it can introduce deadlocks and lack of coordinations. So the reason I'm mentioning this is if we take a few little steps to the future, we're going to see we'll be living in a world with more electric vehicles with self-driving features and more robots in our lives. And at some point, we want to achieve a level of consistencies among these robots. And this level of consistency we're trying to solve is the safety. We want to sort of bring, like have the robot shares a common set of rules that they are able to follow, have the cars able to follow the rules, able to, in specific, they're able to stop before colliding with each other. And to achieve that, the cars have to share their path. Like they have to know the path of other cars, but that's kind of hard to achieve because we're gonna have a lot of robots, a lot of cars from any brand like Tesla and Waymos, and they don't want to sit on the same tables. So our approach is we introducing this hybrid system. This is a new navigation system that take the best part of decentralized and centralized system merged into one. For decentralized, it's like the robot will still be able to follow their path, able to follow what they're planning to do. But also on top of that, there is centralized node. It's gonna see the plan of the robot and it's gonna detect if their plans are doesn't match with the expectations, or in more specific, they will crash. If they do, then this centralized node, we call it the virtual traffic lights, will give signals to the robot so that they can stop before collisions. We have this image of two quite perfect robots in here. Their paths are set to cross, but before they coming to the collision points, one is requested to stop because with the red light, and the other was issued with the green light for permission to move forward. We will get to the deeper layer, like the methodology of the work behind this, the recipe of the dish. But it sounds fancy, but it's actually dead symbols behind the logic. So basically, before each robots are about to navigate, they submit their paths to this virtual traffic lights node. It is like a higher node that process the paths. So they send their paths to this node, right? And then this node will analyze the paths. We will analyze the path of all robots in that deployment. It will see if they're gonna crash some point at the same time in the future. And that's the only thing that the virtual traffic light nodes do. It's only check if the path of which robot's gonna crash, and then the robot don't know about this. And then when they are able to analyze the collision point, we will draw a circle, like you see the red and green circle in there. That is the collision zone, and we can tune the radius of this circle. But when one of these robots is getting closer into this collision zone, the virtual traffic light will issue a full stop on all of the robot, and then it will see which robot comes first, will get the option to move first, while the others have to wait. It's basically following a first in, first out logic. But we can also change this based on our preference as well. And we can change this based on the level of importance of the robots. So once the robot is able to know which one gets to go first, if that robot will proceed to move through the collision zone while the other one waits. Until then, the first robot finished moving, the other robot start moving in the zone safely. And we test our approach on both simulations and real robots. As for simulations, our setup is a small map with turtle plots equipped with LiDAR, and they are on the ACRA global planners. The maps we have pillars as the 9 circle pillars you can see. These pillars, they represent a wall, they form a tight corridor so that the robot cannot pass through each other. And the robots use dynamic windows approach for local collision avoidance. We compare our approach with a fully decentralized navigation, nav stack by default of these robots, and we run it for 1,000 trials with 1 to 10 robots. This is a video of how the simulations is running. So that is 2 robots coming, and then one to stop and give way to the other one. Once it's out of the zone, the other one proceeds moving. And we can scale this up to many robots, but in our simulation we scale it up to 10, depending on the size of the maps. And it's just still following the same logic, first in, first out, and the robot will just stop, wait until it can safely move forward. On the right screen is the logic of movement, and the left is the LiDAR maps. Then once we run through the simulations, we measure the success rate of the robots. Success rate is the percentage of robots that reach the goal within timed out windows. And we have seen that our approach is better than the traditional decentralized systems in terms of able to reach the goals. Apart from this, we also measure the replan rates. Replan is like the total number of paths the robot needs to replan because it got stuck or it's unable to find a better path. The reason we measure replan is because robots work on energy, right? And energy is like food for the robots. We need to save energy as much as possible, and the more numbers, the more replans the robot do, it will consume more energy. So we want less replan as much as possible. And once again, our approach proves that we have fewer replans than decentralized system. And this is our test on real robots. We test on unitary quadruped robots. And in this simulation, the robots know where to go already. They follow this path, and the virtual traffic light just signal them so that they know where to stop and when to stop to give way to other robots. Like in here, that the robot stops to wait till the other robot passes, then it got a green light to And we also test this on Lucky Town and Lucky Box project. Lucky Box is like small self-driving cars following a lane. In here we specify these two robots to cross as well, but they wait and then to wait for the virtual traffic light to give signal to which one will be able to go first, and the other one just wait till that one moving out of the zone and then continue its path. Of course, there are some limitations in future work in this. Currently, the performance is likely become unpredictable at higher densities of robots, and conflict clustering merge nearby intersection into one robot to enter, which we aim to improve in future work, and also average slower than purely decentralized baseline. This is somewhat understandable because it is a trade-off for safety instead of speed, because the robot needs to slow down before it's crushing with the other one. Hence, the speed just decreases. So, to wrap everything up, we are presenting a hybrid navigation strategies with little computation resource, yet proved to be effective. And it is a simple plugin that sits on top of standard navigation across various robot types with proof of concept. You don't need to modify much in the configuration of the robot. Mainly, you just need the path of the robot and then this thing, virtualized system, which is processed on that path only. And as the results, we successfully reduce deadlocks and increase mission success rates. Thanks, everyone.